All right, let's do this. So I have things for you to pass back. The quizzes that you turned in, those summaries about your life. Some of you were very willing to tell me about yourself, and I appreciate that. Others weren't very, let's just say, forthcoming about much of what they are doing, and that's okay. This was just to kind of have an idea of what I'm dealing with here. So I'm just going to pass these back. If you turned it in, you should have some credit. I actually did give people some low scores on this because they actually just did not answer anything, just put their name on it. And so if that's you and you want to talk about it, you can get with me about that. So please go through the stack, get your stuff out of there. And then the other one is the quiz you did in class the other day, right? There's one more in there, sorry. So the quiz you did in class, is it okay if I just pass these around and let you get yours out of here? Does anyone have any objections to that? You sure? No objections? Okay, all right, so this will start over here. All right, so last class we were talking about limits, right? And we were talking about how it is that if somebody presents you with a function, then we can try and find the limit algebraically, right? And so we used several sorts of tricks to do that. Factoring, what else did we do? Factored, we rationalized, multiplied by the conjugate, right? And in the homework you should have had some practice with that. Now we kind of shift gears just a little bit. We're still going to be doing limits algebraically, but we're going to bring in some trig functions. So we have conveniently avoided them up to this point. And we are going to use two of these properties that we have for limits of trig functions. And it's very important that you know these, all right, that you memorize these. Really, the first one is the one that you'll see pop up all over the place. Cal 2, Cal 3, differential equations. This limit seems to just always seem to be there somewhere, all right? So let's discuss this first limit. The limit as x approaches 0 of sine x over x. So I'm telling you right now that the answer to this is what? 1, okay? So if we were to graph this function, it should be approaching 1 as we approach 0 from the left and the right. All right, maybe I'll graph it here in just a second, all right? But let's just first convince ourselves that we could not figure out that the answer is 1 by doing any algebra, all right? So there's nothing we could do to this right now to figure out that the answer is 1. When we look at this, we'd first just check, right? We see what is this doing? So we say, all right, what happens if x approaches 0? So what does the sine function do as you approach 0? So what is sine of 0? 0, right? So if you look at the sine function, right, there's your sine function. Here's 0. If you approach 0 from the right or from the left, right? Sorry, I should be on the function. No matter which way you approach 0, from the left or the right, it's headed to 0, right? So the top is headed to 0, and then of course x itself, as x approaches 0, right? So we get 0 over 0, and we talked about that being bad, right? But there's no algebra we can do here. Right? I mean, is there anything you can do to this? I mean, you can't cancel the x's, right? You can't, right? Okay. So there's nothing we can do. So you're just going to have to take this on faith, right? I'm telling you that's what the limit is. I could graph it. You would be convinced that it's doing that. Now later on, if I have time, which I doubt I will, I can actually show a proof of this, but it's pretty involved. It's very geometric, and then later on, I'll be able to show that it's 1 very easily. So I think I'm just going to wait till later when it's easy to show that this is 1. All right? Now, a little bit more about this limit. This limit is 1 even if you flip it over. So if the x is on top and the sine x is on the bottom, you still get 1. All right? Now let me show you the way that I want you to learn this limit. This is the way it appears in the book. All right? But here's the way I would like for you to think of this limit. This limit is actually saying if you ever take the limit, and it doesn't matter what this limit is down here. Okay, so don't worry so much about this thing right here. All right, like x could be going to 0, it could be going to 2, it could be going to 5, it could be going to whatever. Who cares about this? But let's say you have up here sine, and then inside the sine you have something. I'm going to call it junk. All right, you've got some junk in here, right? And then down here you have the junk. So in this particular version of this, what's the junk? X, right? So it doesn't really even matter what this is. This answer will always be 1 so long as the junk is going to 0. All right, so long as your junk is going to 0 when you take the limit. So let me explain what I mean in a specific example, all right? So I'm going to leave this all up here. So I'm going to do my example over here. Let's say I take the limit as x approaches 2 of sine of x minus 2 over x minus 2. The answer to that should be 1. The reason why is because you got sine of some junk, right? That junk right there is the same as that junk, right? And what happens as x approaches 2? This junk goes to 0, right? And that junk goes to 0. So it falls into this like kind of model, yes? So the answer is 1. All right? Let me give you another example. What about this? Limit x approaches 2 of sine of x minus 2 over x squared minus 4. So how about that? Does that fall into this kind of template that we have? Do we have sine of junk over junk? Does the junk match?
No.
No, the junk doesn't match, does it? See, this junk has to be identical to this junk right here. Are these identical? No, they're not. So you can't use this, right? You can't. However, oh, I should point out that if you let x go to 2 here, right? What happens if x goes to 2? That goes to 0, right? Sine of 0 goes to 0 on top. And then 2 squared minus 4 is still going to 0. So we do have 0 over 0 here, right? So we do have a problem. But we can't go directly to this answer because these two things do not match. They have to be identical. So I'm just going to do a little bit of algebra first. I'm going to realize that the denominator is a difference of squares, right? Do y'all agree with that?
Yes.
Okay, now I will be able to use this, but I still want to try and convince you that I can. And I want to carefully show you how I'm going to do it. So the next line I'm going to write, it's going to look like this. Limit x approaches 2. I'm going to write sine of x minus 2 over x minus 2 times 1 over x plus 2. All right, so is that the same thing? All I've done is I've taken this product down here and I've rearranged it, but I just slid the x plus 2 to the outside as its own little fraction. Do you all see that? So if you put these back together, you get that. But now, do you see that this right here Looks exactly like it needs to look. You've got sine of junk over junk. Does the junk go to 0? Junk goes to 0, junk goes to 0, right? So this piece right here goes to what? 1. So my next line, this is going to go to 1. And so I'm taking the limit right now. So I'm not going to write limit again. So this right here is going to 1 times, now what happens when I let x go to 2 over here? What do I get? 1 over 4. 1/4. So what's the answer? 1/4. Do y'all get this? Yes.
What was the part about the junk going to 0? Like meaning it would cancel
Like,
out? Or?
no. At each, so when I take this limit, okay, so whatever this says, when I actually compute that limit, whatever's in here needs to go to 0.
Gotcha.
Okay? So when we do this part right here, as x goes to 2, that junk is going to 0, right? And that one also. So let's just verify this with the graph. I think what I'm going to do is I'm going to graph the original thing over here. Let me erase a bunch of this. So what I'm going to do is I'm going to graph sine of x minus 2 over x squared minus 4. I'm going to graph that function. And what we should see is that as we approach 2, right, in the graph, as we approach 2 from both sides, our function should be approaching what? 1/4. All right, so let's see if I can get this typed in here. Sine of x minus 2 divided by x squared minus 4. There it is. Now, come over here. Too much. There we go. That's good enough, right? So here's 2, right? Now, what's happening at 2? Like if this is our function, what is f of 2? What is f of 2? No. Can you plug 2 into this function? You cannot, right? So you have a hole there. Now, again, the computer doesn't show holes. No graphing calculator that I've ever seen in my life shows holes, all right? That's because all the calculator does is just plugs in a bunch of points and plots points. So you can't really see holes on graphing calculators. But there is a hole right here, all right? But what we determined is that if we were to look at this graph, that when we look at it, as we approach 2, the y values should be approaching what? 1/4. And you can see that this is, 0.25, right? So from both sides, it's approaching 0.25. Does that making sense? So, but we could do that without the graph. We did it algebraically, right? Okay. All right, so sine of junk over junk, right? But the junk has to go to 0. Sine of junk over junk, but junk has to go to 0. And it can be flipped over, right? That's what I said. I said it is okay if it's the other way around. So if you have junk on top and sine of junk on the bottom, that will also, did I say 0? Yeah. Doesn't go to 0, it goes to 1. Sorry. I think I said 0.
I think you said as long as the junk goes to
As long as the junk goes 0. Okay, all right. So as long as this junk and this junk goes 0, the answer is 1. And if you flip it over, same scenario, you also get 1. All right? That one you need to burn into your brain. Now this one doesn't come up as much, but it is similar to this one in the sense that if you ever see this, let's just see what happens right now if I take this limit. I'm telling you the answer is 0, but let's see what happens when we try and just plug 0 in. What is cosine of 0? 1. So 1 minus 1 on top would give us 0. And on the bottom, of course, if I let x go to 0, that's going to go to 0. So we have a bad situation, right? So at 0, this thing is undefined, but what's happening is we approach 0. It's approaching 0. Now I'm telling you that, right? If you replace this x and this x with junk, so long as the junk goes to 0, the same thing happens. The big difference between this one and this one is that you cannot flip this one over. See how this one I said you could flip it? You are not allowed to flip this one over, all right? So with just these two formulas, we're now about to do a couple of limits that involve trig functions. And hopefully you'll see how this is going to work. This is where the wheels on the bus start to get a little bit wobbly for most people, all right? Maybe not this time. All right, here we go. Limit x goes to 0 of sine x over 5x. So does this look kind of like what we have in our little formula? Yeah? Okay, let's go with Anika. Where's Anika? You're not the math major, right? You are? I got that right? Wow. It's a good day. It's a good day. Okay, so, I also, on some of your things that you filled out, I wrote some little comments on them. You know, some of you I did, some of you I didn't. So if I asked you a question, I'm not expecting an answer, but if you want, you can answer at some point. All right, so what do you see here? Can we use the formula we just got? Yes? So how would we use it? I mean, are you saying that the answer to this is just 1? No. Okay, so it's not 1 because you have to have sine of junk over junk, and the junk has to match, and it doesn't match. So could you somehow massage it and make it right? How is this, okay, what's the problem? What do you wish wasn't here? The 5, right? So this 5 is being multiplied, right? So would this be like a legal move? I mean, is that the same thing? Yeah, right? So because that's the same thing, I can look at these separately. No, I can look at them separately because there was a limit law from last class that if you ever take the limit of two things being multiplied, you can do the limit of each one individually. So the limit of a constant, nothing happens to the constant. And then, what is that? That's going to turn into 1, right? Now, let's be careful here. Anytime we take a limit in this class and we get 0 over 0, what does that mean we have to do? Some algebra, some trick. The only time I've told you right now that you ever see 0 over 0 and get 1 as an answer is if it's sine of junk over junk, okay? So it's not the fact that it's 0 over 0 that makes it 1, it's the fact that it's sine of junk over junk that makes it 1, all right? So this is now just 1/5 times 1, and we're done, right? So the little workaround that we made for that 5 wasn't too bad, right?
Where'd you get the 1 from again?
Pardon?
Where'd you get the 1?
This right here is the formula. That's, right? Look, this is sine of junk over junk. Is the junk going to 0? Is x going to 0? Yeah, that's going to 0, that's going to 0. They're identical. That thing turns into 1 every time. All right, let's compare that to the part B. And I'm going to leave that one up on the board, and I'm going to write this one over here. Limit x approaches 0 of sine of 5x over x. All right, so let's see. Where did I put Annika? All right. Jasmine? Okay, so what's the big difference between this one and the previous one?
The 5 is
I'm sorry?
the 5 is on top.
The 5 is on top, right? Okay, so can we do this the same way?
Probably not.
Probably not. What do y'all think? Can you just pull the 5 out of a sine? Absolutely not. Okay? Now here it was this one was multiplication, so I could just pull that 5 away. This is not multiplication, right? This is sine of 5x, not times 5x. So that thing there, which we call the argument is the thing that's inside the function. The argument of that function is 5x, and we hopefully learned in pre-cal that you cannot pull constants out of arguments of trig functions. So you are stuck with that 5. You can't change it. So if you can't change it, you can't move that out, then what would you really love to have had down here? A 5x, right? So there's not a 5x. But now we're going to make a 5x. So what we're going to do is we're just going to be clever here. We're going to multiply by 1. You can always multiply something by 1, right? Without changing it. So the one that Jasmine's going to pick is going to be a very special one. So what is the 1 that I'm going to multiply by here? What do I want here? Okay, so what should you introduce? A 5 on the top and the bottom, right? I've introduced that. I've decided that I need the 5x, so I introduce a 5 over 5. Now that 5 on the bottom can slide over next to the x. And what do I still have over here? 5 over 1. Or just 5 if you want. Right? So all I've done is just used a little bit of algebra and a little bit of brain power, right, to generate what I needed. And now, Herman, where's Herman? So what happens now?
Sine 5x over 5x should equal to 1.
That should go to 1, right? Sine of junk over junk. The junk is going to 0, right? Because as x goes to 0, 5 times 0 is still 0. So we get sine of junk over junk. The junk goes to 0, so you get 1 there. And then you still have out here 5, so your answer is 5. Done. Do you see the difference between these two problems? This one was just pull the 5 to the side. That one we had to introduce something to make it work. All right, let's see who the lucky one here is. Luke? All right, Luke. So Luke, we always want to check first to see what's happening, right, to our limit. You always want to just try and let x go to 0 and just see what happens. So do you remember, Luke, if x goes to 0, 5 times 0 is 0, what's tangent of 0? Do you remember what the graph of tangent looks like? This look familiar? That's tangent. So what's tangent of 0? 0, right? Okay. So for everyone in here, you must know what sine, cosine, and tangent look like. It should not be something that that is a true prerequisite of the course. You can't be in here wondering what cosine of pi over 2 is and going back and looking into your pre-cal notes. Like you just need to go brush up and do it fast, all right? Okay, so this tangent of 0 is going to be 0. So the top is headed to 0, the bottom also headed to 0. So we have a bad situation, right? Now, Luke would agree with me, I think, that we can't use the formula I just gave you because there's not a sine, right? It's tangent. However, tangent is what? Sine over cosine. So would it make sense that maybe we should rewrite this as sine x over cosine x so that we can use the formula? All right. So this is limit x goes to 0. Let me write it this way first, just so you can see kind of what I'm doing here. Okay, so we agree with that. Just kind of splitting it up. That's the same as tangent 5x over x. And now I'm going to rewrite the tangent x of 5x as sine of 5x over cosine of 5x times 1 over x. So that's still just rewriting everything, right? All right. Sienna? when you look at this, right? If you start letting x go to 0, this top goes to 0. What's cosine of 0? 1. So this is 0 over 1, right? That's not a problem. This is not a problem, right? But then we have 1 over 0. Like, that's where we have a problem. We have division by 0 right here. So how can we be smart and use what we're started class with to somehow eliminate this as a problem? Do you see it all? Where to go with this?
No.
Okay. Do you see you have sine of some junk right here? You see sine of junk? So what would you need to have underneath this sine of 5x in order to make it turn into a 1? What would you, well, yes, but to use the formula from the limit. 5x, right? You need 5x's. You have an x, right? You don't have 5x. So this is kind of the same game we just played, isn't it? I'm going to introduce something over here. 5 over 5. All right, now I'm going to rewrite the problem. All right, I'm just going to rewrite everything. This becomes limit x approaches 0. Watch this. Sine 5x over 5x times 1 over cosine 5x times 5 over 1. Is that the same thing? So all I'm doing is using the fact that with multiplication we can rearrange, right? So we decided to basically take this guy and like just move him over, right? We took the x and we took the 5 and we slid it underneath this sine 5x. We slid this one to the side and we left that 5 up top, right? Any questions on that? And you see what's going to happen to everything? If we take the limit now, this does something nice, right? This goes to 1 times 1 over, what did we say cosine of 0 would be? 1 times 5. So the answer to this one happens to be 5 also. The last one was 5, this one's 5. So I say that this is where the wheels on the bus starts to get wobbly for a lot of students, because it's kind of one of those times in math where it's not just me providing you a formula and saying go do this formula. Like, you actually have to understand what you're trying to do. Like, what you're trying to exploit the formula, right, to somehow get to this solution. And so to exploit the formula, or you're trying to exploit the problem using the formula, and so you have to be clever. All right, let's see the next one. Elijah? Where's Elijah? Okay. Are you following so far, Elijah?
Yes.
Okay, good. So what do we always check first, Elijah? Just to see what we have, right? Just see what's going on here. So if x approaches 0 here, right? If x approaches 0, then that's going to be 0. So I'm going to write this down. This is approaching 0 times, and now you have to know what cotangent of 0 is. And that may not be something that people know. I expect that you know sine, cosine, tangent, like right off the top of your head, but maybe cotangent's not as easy. So maybe you don't know what it looks like, but do you know what cotangent is? Like, tangent was sine over cosine, right? So what's cotangent? The other way around. So I'm still not sure what's happening here, but I know I can rewrite this as cosine x over sine x, right? Now maybe we can determine what's happening. If you let x go to 0, we said that's going to 0, right? What about this? Cosine of 0 is 1 over sine of 0 is 0. So do we have 0 over 0? We do, because this top is going to be 0 and then over 0. So we have a bad situation. We need to do some sort of algebra, some sort of trick. Elijah, do you see it? Do you see the formula that we need to all know now? That's the same thing, right? Just slid this under here. Now, this is backwards, right? It's upside down. But I said, starting out, it's the same thing. You get the same thing when you flip it over. So now we can take a limit, right? So this limit will go to what? 1, and then times, what's cosine of 0? That's going to be 1 also. So the answer to this is 1. So if we graph this function, as you approach 0 from both sides, the function will be approaching 1. At 0, it would be undefined. This one will be fun. Yes?
Do you ever have these problems where it only approaches from one side?
Yes. We are going to discuss that. Yep. The question was, do we ever have problems where you do limits where you only approach from one side, not both? And the answer is yes. All right, take a look at this one. Danielle. Do we have 2 Danielles? We do? Danielle B. Okay, there you are. I didn't see you there. You're up. Are you following this so far? Okay, good. So you get this one then. Yay for you. So let's just check first what's happening as t goes to 0, right? Remember the top really means, right? That's the notation. That little squared here means you take sine of t first, then square the answer, right? So what is our top heading towards, Danielle? 0, and the bottom is headed towards 0. Okay, so we are in a situation where we have to do something. Algebra, some trick. Do you see it, Danielle? What's different about this problem compared to them? It's being squared, right? Wouldn't you really like it to just be sine? Just sine t? Because you already have a t on the bottom, don't you? So just make it sine t. How about just rewriting it as sine t over t times sine t? Isn't that the same thing? That's the same thing, right? Do y'all agree with that? Okay, so if that's what it is, then Danielle, what does this first thing go to? It goes to 1, right? So I can say that this goes to 1, and then times, now sine of 0 is going to be 0 again, right? But this time it's not division by 0. This is 1 times 0. This is 0. So the answer is 0. Does that seem too easy? Why do I have C down there? I don't know why I have C. Oops. We're going to skip F and come back to it, all right? Oops. All right, so let's take a look at this one. All right. Arturo. So far you're okay with this? Yeah. Okay. So we always check first to see what's happening, right? So as x goes to 0, what does the numerator go to, Arturo? If you replace x with 0 up top, you're going to get tangent of 0, right? Yep. And we just said tangent of 0, 0. So the top is headed towards 0. The bottom is going to be sine of 0, which is still 0. So we have a problem, right? All right. Any ideas? Okay, so let's convert the tangent into sine over cosine. That seems to work. That seems to have helped us. Okay, so I'm going to do this kind of in slower steps here. I'm going to rewrite this as tangent 3x times 1 over sine 6x, right? And now I'll convert my tangent into sine over cosine. So this is going to be limit x goes to 0, sine 3x over cosine 3x times 1 over sine 6x. And I think I'm going to go one more step. Limit x goes to 0. Watch this. Sine 3x over 1 times 1 over cosine 3x times 1 over sine 6x. So all I did there was just pull these two apart into two fractions, right? All right, so Arturo, I have an important question for you here, Arturo. Which of these three factors is causing the problem? So like as x goes to 0 right now, is this factor a problem? No, because you get 0 over 1, and that's 0, right? Is this factor a problem? 1 over cosine of 0 would be 1. So 1 over 1, that's not a problem. And here you get 1 over sine of 0. Sine of 0 is 0. So here's the problem, right? This is the issue right here. You would need what up here? Not 6. You need 6x, right? You need the whole junk, not just the number. So do you all agree we have to introduce a 6x up top? But you can't just throw a 6x up top. Whatever you do on top, you have to do on the bottom. So here we go. I'm going to introduce, or Arturo suggested we introduce a 6x on the top and a 6x on the bottom. Now we'll be able to take this 6x and we'll be able to plop it right there, and then this will no longer be a problem. Do you all agree? Okay. So let's just run through it real quick again. This is not a problem. This is not a problem. This won't be a problem anymore. But this now will be a problem. Because we'll have 6x on the bottom again, right? And as x goes to 0, you're going to get division by 0. So it's almost like I always envision like a boat with like a hole in it, and you got water coming in. You like plug it up, and then water starts coming in another hole. And so like we plug this hole, and then a new hole sprang up here, right? How can we be clever about this? Because this is a problem. 6x is a problem. Does anyone see it? What do you mean? But if you can't just come in and divide this by 6x. You'd have to divide the top and bottom by 6x. Does anyone see it?
Multiply the sine.
How do you mean? I think you're on the right track.
Break
How
down
do you?
6x.
Okay, so like if this were a 6x in here, that would solve our problem, wouldn't it? If that was a 6x, then we would have this 6x, right? Yes and no. It's hard to make this a 6x because you can't just multiply by 2. Right? If I multiply by 2 here and here, like you can't pass the 2 in. But you're on the right track. You're on the right track. You're almost to it, actually. Ah, okay. So look, here's the way I look at it. Everyone's going to kind of have a different perspective on this. This 6 is times x, isn't it? And everything down here is multiplied. So that x, I can put it anywhere I want. So what if I just took the x and slid it under here? I would almost be there, wouldn't I? What would I still need? A 3. But I can introduce a 3 by doing 3 over 3. Now, you could have broken the 6 down to be 2 times 3, but if that was a 5, you wouldn't be able to do that. So I'm just going to introduce a 3 over 3 now. And then I'm going to take the 3 on the bottom, I'm going to slide it under here, and it's going to now create the 3x I need. Look, I'm only here, I'm the messenger, okay? This is the way it goes, okay? So let's rewrite the whole problem. We have limit x is approaching 0. What does my first factor become? Sine of 3x over 3x times, did we even touch this one? No. 1 over cosine 3x times, now this one, remember, We took the 6x and we popped it over here, so we have 6x over sine 6x. And then times, let's see, what went away? This was gone, right? What else was gone from this? The x went away, right? It's over there now. And so the only thing left here is what? A 6 on the bottom, right? So 1 over 6 times, and then over here, which one moved? The bottom 3, which leaves me with the 3 that's still on top. So I have 3 over 1. And now, if we take our limit, everything should be okay. What is this going to go to? 1 times, what is 1 over cosine of 0? Cosine of 0 is 1, so that's 1. Times, what is 6x over sine of 6x? If the junk matches and the junk goes to 0, 1. And then these are just numbers, 1/6 times 3 over 1. So your answer is 3/6, which is 1/2. The limit is 1/2. Do you see what I mean by these aren't very like natural problems? You have to kind of know what you're trying to do. Okay. So in your homework, there's a few problems like this. And I always give one of these on the test, always. Okay, because I want to make sure you understand this thing. Do I need to run through this at all? Is everyone clear on it?
Just thinking basically, because everything's being multiplied anyway,
Mm-hmm.
you can just literally just take it anywhere you want.
Yeah, you can take, well, you just can't push them into the trig functions, but you can put them in front. And you can slide it, just slides around the denominator, numerator, wherever you want them. As long as you're multiplying, right? Multiplication can do that. All right, let's look at number f. Let's look at f. And f is different. There's one problem in your homework that I'm not going to show you how to even go about it. I want to see if anyone can get it. It's weird. It's a weird problem. So if you get to it in your homework, you'll probably know you're there because it'll be very confusing. So see how you do with it. All right, limit. Where is x approaching here? Pi over 4, not 0, okay? So it's approaching pi over 4. 1 minus tangent x over sine x minus cosine x. So we always check first what's happening. So we all know, of course, that tangent of pi over 4 is 1. So 1 minus 1 is 0. I'm saying that with a little giggle as I say it. Tangent of pi over 4 is 1, right? Okay, what is sine of pi over 4? Root 2 over 2 minus cosine of pi over 4. Root 2 over 2. So we have 0 on the bottom also. So this thing is approaching 0 over 0, which means we have an issue, right? All right, so you start sitting going, okay, I'm going to use that whole sine junk over junk thing. Maybe you start thinking that, right? But you can't. Why can't you use sine of junk over junk, Omar? Why will the sine junk over junk not work in this problem?
You have a tangent on top.
Okay.
So then it means subtracted by 1.
Okay.
You have to have a common denominator on top to subtract those two values.
Okay, so I think what you're doing is you're starting to give me an idea of how I can approach this. My question though is, why would I not be thinking sine junk over junk here? Remember, we need the junk to go to what? The junk has to go to 0, right? So as x goes to pi over 4, sine of junk, that's not going to 0, is it? It's going to pi over 4. So this does not fall within the scope of what we've been doing. Does that make sense? So we need a different sort of approach. And that's why this problem was thrown in here. It's like we don't want to get our focus too narrow and think everything's going to be sine junk over junk every time. This problem we can do without sine junk over junk. We just have to do a little bit of algebra first. So you suggested something about, what were you saying?
Well, turn the tangent of x to
Okay, yeah, let's do that. So you're going to turn that tangent x into sine x over cosine x. And that's perfectly legal for you to do that. Okay, did you have a purpose now, what you want to do with that?
Yeah, then you multiply the left side, the 1 by cosine x.
Okay, so are you going to put those together?
Yes.
Okay, so you're going to get a common denominator here.
Right.
So you're going to rewrite 1 as cosine x over cosine x. Okay, everyone agree? That'll work. Limit x approaches pi over 4. Can I ask you, Omar, why you're doing that? I'm trying to ask this question because I'm sure there's a student in here going, why in the world is he doing that?
I guess to simplify it.
Okay, it looks more complicated to me. I'm just challenging, yeah.
Well, then I would multiply by the reciprocal to simplify it.
Okay, so I'm going to help answer that question the way that I want it answered. All right, and that is, what else are you going to do? I mean, if you're sitting here looking at this and you don't know what it does, you've got to try something, right? You've got to do something. So rewriting tangent as sine over cosine is something, and getting a common denominator is something. The other option is just stand there and look at it, and then decide that you're going to go and do something else instead of your math homework, right? Like you have to try something. So this is just algebra to hopefully get us somewhere. And it's going to work, all right? So now at this point, let's just put these together. It's like, I'm really bad with analogies. But I'm not a baseball, like I didn't play a lot of baseball as a kid. But I did play, but I knew I was never gonna like actually get a hit if I didn't take a swing. You know what I'm saying? Like you have to take a swing. And in this class, you have to take swings. In Cal 2, have y'all seen that movie? What's that movie with the aliens and at the end the guy's hitting the glasses of water? Signs, that movie. Like in Cal 2, you got to be like that. You just got to be swinging at everything. And you got to be ready to fall and get back up and fall and get back up. And this class is where we really start to try to get used to that idea. All right. I hope I'm making sense. Did that get us anywhere? Omar, I'm going to move away from you because I've already picked on you. Al, you're up. So did Omar get us anywhere here, Al?
Yes. Well, since I'm dividing, there's this big ass line.
Right here, this big division, right?
So I can go ahead and multiply by the reciprocal.
Okay, so you're looking at this bottom one as being a fraction like this.
Yes, sir.
So a fraction over a fraction. So you're saying you can multiply by a reciprocal. And okay, I'll do that. But I think, Al, you're seeing ahead of time here that's going to be a good thing, right? That there's something that's going to happen when I do that. Cosine x minus sine x over cosine x times, see the reciprocal of the bottom, so the 1's on top now, and this sine x minus cosine x is here. Do y'all see it? What is it, Al?
I'll just go ahead and take a negative, typewriter negative.
There you go. Yep.
Either from the top
Mm-hmm.
or from where I just put.
Yeah, so these are almost the same. So they almost just reduce out, except they're off by a sign. And we've seen this before when we've factored, that things are off by a sign. We just pull a negative out and we can cancel out. So I'm going to do that now. I'm going to pull a negative from here. I'll do it in a different color so everyone understands. I'm pulling a negative just out of the bottom one here, which makes that negative and that positive. And now these will reduce or cancel if you like. So Al, what would my next line read? I still have limit in front, right? So what am I left with here?
You're left with 1
1 on top,
over cosine x.
okay? And that negative we pulled, right, is like a negative 1. So I'm just going to put negative cosine x. All right, so don't forget that negative is like a negative 1. And so it's sitting there, it's going to be multiplied times that cosine x. And now let's let x go to pi over 4. And cosine of pi over 4 is root 2 over 2. And it's negative. So we get, now no more limit, right? No more limit. 1 over negative root 2 over 2. And that, anytime you have 1 over a fraction, you can just flip it, right? So this is actually just what? Negative 2 over root 2, right? You got a what? I'm so happy you said that, Jackson. So happy. Jackson says that we have to rationalize that. Do we have to? Do we have to?
By standard like pre-cal simplifications, yeah.
By the standards of pre-cal? I don't know. I'm happy with this. Who told you you had to rationalize? Everyone told you that, right? Everybody tells you you can't leave a root in the denominator, right? So let's do a little exercise here. I was going to do this, so I'm so glad you said that, Jackson. We're done, right? That's the answer? It's still up in the air whether or not we have to rationalize that, all right? So someone break out a calculator, and let's forget the negative. Let's just take a look at this right here. Okay, let's just take a look at that. I'm being told that I have to rationalize this, which means I need to do what? Multiply the top and bottom by square root of 2. And that's because you've been told that you are never, ever, ever supposed to leave a radical in the denominator, yes? Okay, so you do that, and on top you get 2 root 2. And what do you get on the bottom? 2, and then, hey, those 2's cancel, so you just get root 2 here, right? So I want someone on their calculator to do 2 divided by root 2. And I want someone on their calculator to do root 2. And what are they going to get? The same answer, right? So if they're the same numerical value, why are you being told, why would you be told that this is incorrect and that you must do this? Why? Why do you think that is? I mean, it bothered me when I was learning. It's prettier, it's nicer looking maybe. It's not good enough. I don't like that answer. So there's a reason why, and I want to explain it to you, all right? So here's the reason why. There was a day before computers. There was a day before calculators, right? And so these numbers that would come up in mathematics that we use a lot, they would have to be memorized. So like if you were back in school back in the 40s and 50s, 1940s, 1950s, you would be, like that number pi, you would just have to memorize it. This is approximately 3.1415, and it keeps going forever, right? Never stops, never has a pattern to it. That's an irrational number. And so there was actually like contests, you know? It was a measurement of like how big of a math dork you actually were, how far you could memorize these numbers. Like, I have a colleague of mine who claims that he memorized that 120 digits out. And I believe it because he can still do it 60 digits out without even thinking about it. So he was in school in the 50s, 40s era, right? And then there's other numbers like that. Square root of 2 is another example. It's 1.414, and it keeps going forever, no pattern to it, it's irrational. Okay, so they had to memorize these, all right? So let's say you're back in a class, no calculators there, and let's say you run into this problem right here. You run into the problem where you have 2 over root 2, all right? Let's say you have to calculate that, this right here. So how are you going to do it back in the old days? You're going to do good old division. You're going to make a division bar. What's going to go on the inside? 2, right? What's going to go on the outside? Root 2. Now what's root 2? Well, you had to memorize that, right? So it's going to be like 1.414, something like that, right? How do you divide that into this? It seems somewhat complicated, doesn't it? Doesn't it seem complicated? So what would be preferred here is if it were somehow the other way around. If the thing with the repeating decimal was in here and the thing outside was a number. Does that make sense? So this turns out to be a bad example because of what happens here. Let me give you a slightly different illustration. Let's say we were doing 1 over root 2. This one will work better. That right there, okay? If I rationalize that, I multiply the top and bottom by root 2, right? And you would get root 2 over 2. So these are identical, aren't they? These are the same numbers. If you do that old school way, you have 1 here and you have root 2 on the outside, 1.414. If you do it this way, then what's on the inside? 1.414, and what's on the outside? 2. Now which of these is easier? The bottom one, because you can say 2 doesn't go into 1, but 2 goes into 14, and then you start working through this, right? Do you see how that works better because you don't have all these decimals here? That's the reason why. Rationalizing the denominator was for, before calculators, we never wanted to have that as our divisor when we had to do long division by hand. It makes sense, right? But now, what is it, 2002, right? We can, right? I mean, it's not needed anymore, right? Now, the actual process of rationalizing, like the mechanics of it, is important. But at the end of the day, that answer is completely valid, all right? So we're just going to leave it. So you don't need to rationalize your answers in here, all right? All right, we are moving on. Yep, did that one. So I'm going to change the order in which we do things. We are supposed to go, we're in chapter 1, section 4. We're supposed to obviously go to chapter 1, section 5. But I'm going to do chapter 1, section 6 first. And the reason is because 1.5 deals with this thing called continuity, which almost feels like, you know, we've been on this road with limits, right? Continuity seems like we take a detour, we go off, and then in 1.6 we come back on. And I think we just stay on the highway and we'll make our exit later, okay? So I think it'll flow better if we just do 1.6 now, all right? So we're still doing limits, all right? Still doing limits. But now we get to play with infinity. So maybe we should talk about infinity briefly before we get into this. So what is infinity? It's a concept, right? It's an idea, right? Infinity. Why do you think they use that symbol? Anyone know why? Where that symbol comes from?
There's no start or end.
Yeah, it's like no start or end, yeah. It's like if you follow it, just, you know. Lazy 8. This is what some math dorks call that lazy 8. Infinity, right? Haha, funny. Okay, so the idea of infinity comes from that picture. Comes from something called a Mobius strip. Y'all ever heard of a Mobius strip? Yeah. So this little strip of paper, we could say has 2 sides to it, right? You have 2 sides. So if you take this strip of paper and you just connect these 2 ends together like that, you still have 2 sides, right? My thumb and my index finger are on the 2 sides. But if instead before you put them together, you twist it one time and then put them together, you get what's called a Mobius strip. And this strip, if you follow your thumb around, you're going to wind up on the same side that your finger's on, and then you come back around and you're back to your thumb, which means that my thumb and my index finger are on the same side of this sheet, which means this is an example of a single-sided sheet, a surface with one side. And it kind of looks like infinity, yes, a little bit, okay? So if you started walking on this, like a little ant, you just keep walking along, and you'd be on the same side the whole time. Interesting little shape. All right, so infinity. Let me give you an example of infinity when we've used it. If you were to, sorry, let me be a little more accurate there. All the counting numbers, 1, 2, 3.